myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we will do Microwave Measurement Part 1. So, before moving towards the measurement section, that is the first topic is the insertion, measurement of insertion laws. First of all, let us discuss what is meant by the measurement in the microwave and what is the significance of measurement in the microwave. So, we always used to do the measurement in the microwave, and that is a very important section in your course perspective because it comprises the lab section of the microwave and radar engineering. So, and the application point of view, microwave measurement is a very important section because any device which we are going to use for the microwave communication system has to be measured for its losses or other parameters so that it can be effectively used for the practical application. So, microwave measurement plays a very significant role because it decides how capable the particular component or particular device is used for the practical application. The first thing which we are going to study is the measurement of insertion loss. The insertion loss is the parameter, very important parameter in the case of a transmission system, and it is defined as the sum of power reflected by the device due to mismatch and the power attenuated by the device. So, what we will say that if there is some device and we want to have its insertion loss, so it can be calculated by measuring the power reflected by the device and the power attenuated by the device. So, first of all think what is the power reflected and why it is the word the mismatch is enclosed here. So, already number of times we have discussed in our microwave section that when there is a device and that is the at the output something, and if the output having the impedance of ZL and the device which is having having the impedance of ZS. So, if ZS is not equal to ZL, this gives the condition of the mismatch. This is called the condition of mismatch, and when ZS is equal to ZL, this is called the condition of perfectly matched. So, when the system is perfectly matched, in that case there is no reflection. And when there is a mismatch, reflection occurs. This reflection occurs and it depends upon the amount of mismatch between the ZS and ZL. If the mismatch is very much high, in that case reflection will also go up, and if the mismatch is less, then reflection will go on the downward side. So, the mismatch basically decide the reflection which can be achieved, and when on the basis of this we can calculate the power reflected by the device due to the mismatch. So, for measuring the insertion loss, what we have to find out first? We have to find out the power reflected by the device. The second thing is the power attenuated by the device. So, what is the power attenuated by the device? Say, the power attenuated by the device, that means whenever, for example, let us see, when we say you have studied about the devices and when we say 20 dB and when you say 3 dB, that means what we are 3 dB down, it means whatever be the particular power level of the device is down to a particular level. So, by what parameter it is down? it is calculated at the power attenuated. So, signal level by how much parameters, how much value it is comes to a lower side is basically our power attenuated. So, if we say 20 dB attenuated, that means power level, what is the whatever be the initial power level of the signal is attenuated by 20 dB. And if we say 3 dB, that means whatever will the initial power is attenuated by a 3 dB. So, basically at that section we are saying that if a signal particular get pass through the our device, and if it is having Pi power at the initial age, and after passing through the our device under test, that is the DUT, its power comes to 20 and a P naught. So, we calculate P naught upon 20, 10 log the base 10 P naught upon Pi, and it gives the power attenuated. So, for measuring the insertion loss, we have to measure this two particular thing. First is the power reflected by the device and the second one is the power attenuated by the device, and both of this can be of course measured by two different method, and whenever we get these two parameters, we will able to calculate the insertion loss, because the insertion loss is defined as the sum of power reflected by the device due to mismatch and the power attenuated by the device. So, what we will do? Power attenuated is measured using RF substitution method and the power reflected is measured using reflectometer. Now, first of all is the RF substitution method. So, RF substitution method is used for measuring the attenuation. So, for this what we have to do? We have to set up this, and this is set up is made in the microwave test bench, which is available in all the labs. It will be available in your lab also. So, what will be the parts of the our test bench which will used for the measurement of our attenuation? First of all, a microwave source, then a attenuator, then frequency meter, and now comes the network whose attenuation has to be measured. So, if we want to measure the attenuation of a particular device, that should be included here. And now, the slotted line and termination has to be there, and other section of the slotted line there is a crystal detector, thermistor mount and a power meter. So, what is done in the setup A? The power output power P is measured through the power meter by including the network whose attenuation is to be measured. The network group should be remain same, and we have to measure see the power at the power meter. Now, this network is then replaced by precision calibrated attenuator. The network whose attenuation is to be measured is now replaced by variable precision attenuator, which is adjusted to obtain the same power P. Already we have measured the power of the network whose attenuation has to be measured. So, we will adjust the power to that level. If that power is P1 at the setup 1, we will adjust the power till this power meter is showing a power same as P1, adjusted to obtain the same power as measured in the setup A. Under this condition, the attenuation read on the precision attenuator would be attenuation of the network directly, and when we adjust the power to the same level, whatever be the attenuation value which can be read out at the variable precision attenuator will be the attenuation value of our network whose attenuation we are about to measure. Now, so in this way we have calculated the attenuated power. Now, we have to calculate the or measure the reflected power, and that is done with the help of a reflectometer. In this method, what we are doing? We are actually using two directional couplers which are identical but differ in directions are taken. Two directional couplers are used which are identical but differs in directions. So, you are already known with the coupler. Coupler is basically a 4-port device. Already we have studied that in the unit 1 of the microwave engineering subject. The two couplers are used in the sampling the incident power Pi and the reflected power Pr from the load. The reflectometer is connected as shown in the figure. It is used to obtain the magnitude of the reflection coefficient rho. Now, this is the arrangement of the reflectometer for measuring the reflected power. So, what we are seeking? Again, the setup has been arranged, microwave source, attenuator. All this arrangement and all this setup is done on the microwave test bench. So, if you want to do it practically, you can definitely do it on your lab also. Microwave source, attenuators to lower down the signal level. Then a forward directional coupler of 20 dB. That means, what is meant by the 20 dB directional coupler? That means, whenever we measure the coupled power of the directional coupler, that will be 20 dB down from the original power which is incident on this directional coupler. So, 20 dB directional coupler means ki at the coupled output we will have a 20 degree down value of the power as initially received by the directional coupler. So, do not get confused what is meant by the directional coupler. Means at the coupled output we will have a 20 dB down power as initially received by the directional coupler. This is a simple definition of our directional coupler. Now, a reverse directional coupler has been taken of the same, what we have said, same directional coupler but different direction. So, this is the forward directional coupler, this is the reverse directional coupler and both is of 20 dB and a load is connected here. So, what is going to have this? Forward detector is connected to the forward directional coupler and reverse detector are connected to the reverse directional coupler. So, at this point we are able to get Pi upon 100 and at this point we are getting Pr upon 100 at the reverse detector and both of this is taken into the reflectometer and reflectometer will give our reflection coefficient and reflection coefficient is equal to under root of reflected power upon incident power and this reflection coefficient values can be obtained by this and if we are available with the reflection coefficient value, we can definitely know the incident power which is that can be easily calculated by anyone and easily can be known by anyone. What power we are going to give in this circuit. So, now through reflectometer we are able to calculate the rho which is our reflection coefficient and we have to calculate the reflected power and incident power. We can have initially what power we are giving it so as to obtain the reflection coefficient value which is obtained by the reflectometer and through that we are able to calculate the reflected power. So, after getting the reflected power through the reflectometer and getting the attenuated power from the RF substitution method, when we sum it up we will able to get our insertion loss. So, through this method we are able to calculate the insertion loss. Now, the second measurement, that is the frequency measurement, at which frequency our microwave device is working. A frequency, of course, in the microwave system frequency plays a very significant role. So, it can be calculated by two methods. First one is the slotted line method which is our indirect method and second is the resonant cavity method, that is our direct method. So, let us for the, you have seen here in the RF substitution method you are seeing the frequency meter that gives the direct measurement of the our frequency and that is basically a resonant cavity method. And you are able to see your frequency meter all the setup of microwave test bench which is available in your lab. which is our cylindrical structure which is sort of a cavity and which directly gives the frequency measurement. At what frequency the microwave test bench is working. So, first of all we will have the indirect method of frequency measurement, that is the slotted line method, and for that what we will do, the standing wave set up in the transmission line or a waveguide that produce minima for every half wavelength apart. So, what is the concept behind using the slotted line method? That we are particularly setting a setup like this, where we have a signal generator, of course a microwave signal generator, a variable attenuator in every microwave test bench. This is the general setup. We have seen that in the RF substitution method also, because this is the basic things. Then a frequency meter, slotted line, crystal detector probe, crystal detector mount, SWR indicator and a match termination. SWR is our standing wave ratio meter. Indicator which basically shows the value of standing wave, and for your recall I am just going to tell you incident wave, if we are assuming this as an incident wave, and if there is a mismatch between the initial end and the output end, the wave will be reflected, and when the incident wave and reflected wave combines to give the standing wave. So, this concept of standing wave are taken into consideration for calculation of the frequency in the case of an indirect method of frequency measurement. And another thing, for each half wavelength we are able to get this type of maxima or minima. So, if we are taking the maxima, we are taking the maxima only, and if we are taking the minima, we take the adjacent minimas. So, what we are doing, the first thing we are doing, the minima are detected and distance between them is measured. So, two adjacent minimas are detected in the SWR. When you see the SWR meter, that is our standing wave ratio indicator or meter, first when you move the slotted line, what we are doing to do this in this case particularly, basically we are, this is the slotted line which we can move, and when we move the slotted line, what will happen? First minima, we just note the value at the which section point of the slotted line we are getting the first minima, and minima can be obtained in the SWR meter. Then we again move the slotted line, first we are getting at the D1 point and second we are getting that at the D2. So, that two values are noted down, and from that we are able to get the our lambda g. So, now we have to calculate the frequency. So, frequency can be calculated by c upon lambda naught, where c is the speed of the light. Now, we have to know the lambda naught for calculating the frequency, and lambda naught required lambda g, lambda c, lambda g square, that means basically lambda g and lambda c. Lambda g can be calculated from the two adjacent minimas. Now, we have to know the lambda c, and this is the cutoff wavelength, and we know for the TE10 mode, which is the dominant mode, our cutoff frequency is given by c upon 2a. So, from that we are able to get our lambda c, then lambda c will be equal to what? C upon fc. So, we are available with our lambda c now, because A is the broader width of the waveguide which we are using in our measurement purpose, and that we can get that value from the parameters or the specification of the device. So, we are available with lambda g and lambda c both, and from that we are able to calculate the lambda naught, and getting the lambda naught value we are able to calculate the frequency at which our device or the setup is working. So, this is the method of the frequency measurement by slotted line method. Now, we are moving towards the direct method, that with the help of a resonant cavity method. This is the most commonly used microwave frequency meter, and it is the wave meter. It is a cylindrical or coaxial resonator. Already we have studied that we have a waveguide of two type, circular and the rectangular, and from the we have a waveguide of a two type, we have a resonator of a two type, rectangular and circular, and cylindrical basically. Circular, in the case of a circular we say the cylindrical. So, cylindrical we have a resonator, and that resonator is used further modified to get the frequency meter. And it is designed in such a way that for a given position of the plunger is inserted in this, and for the and it is a movable plunger, and for the movable plunger it adjusted at for any given position of the plunger, the fixed frequency our cavity will resonate at only one frequency, and if we move the plunger, it gets shifted, frequencies also get shifted. So, this is a cavity, and where plunger are inserted, which is a movable one, and whenever we move the plunger, our frequency changes occur, and at a particular position of a plunger only one frequency is operational. So, through this way we are able to get the frequency measurement with the help of a resonant cavity method, which is a direct method of calculation of the frequency. Now, one of the most important factor, that is the measurement of a Q of a cavity resonator. The Q stand for the quality factor, and there are three methods of measuring the Q of a cavity resonator. First one is the transmission method, second one is the impedance method, third one is the transient decay or the decrement method. And upon this, the transmission method is the simplest one, and which we are going to study in this particular lecture. This is the setup of a measurement of a quality factor of a cavity resonator, and first setup is like this: microwave source, attenuator, cavity resonator, detector and the power indicator. So, in this method what we are going to do? In this method, the cavity resonator acts as a device that transmit. The output signal is plotted as a function of the frequency, which result in the resonant curve. Whatever output we are able to achieve is plotted as a function of frequency. So, the plotting is like this. What is we are getting at the output? Output is giving the basically the power. So, basically frequency is plotted as the function of the frequency is plotted as a function of a power output, and that power output in the dV. So, this type of curve we are getting, and since it is a resonant cavity resonator so this curve is called as the resonance curve. And from the above setup, signal frequency of the microwave source is varied, and this plot is basically achieved. Signal frequency is varied, and whatever power we are getting is plotted in the form of this curve. What is now going to happen? Keeping the signal level constant, signal level is kept constant at this point and at this point, and then the output power is measured. When we are going to make the signal frequency constant, signal level constant, and the output power is measured, the resonant frequency is tuned to this frequency, and the signal level and the output power is again measured, noted down to know the difference. At this frequency signal level we have phase fixing, and again we keep on changing the frequency, and we are noting at which power we are actually getting the same signal level, and the difference is given by 2 del. Now, this 2 del is equal to what? Is equal to plus minus of 1 upon QL, where QL is the loaded value of the quality factor, and QL is equal to plus minus 1 upon 2 del is equal to plus minus omega upon 2 within bracket omega minus omega naught. If the coupling between microwave source and the quality and the cavity and between the detector and the cavity are neglected, then QL is equal to Q naught, which is our unloaded Q. So, for the accuracy of this method, what we are able to do, we have to repeat this so as to get the actual value, and this second one is in case of a very high Q, this poor method, so a very less accuracy in the case of a very high Q, because at this time narrow band of operation is achieved. So, this method gives a good accuracy for the low value of the Q, and for this the resonance curves plays a very important role. So, in this section what we have concluded, we have learned the measurement of insertion loss, and while measuring the insertion loss, we of course come to the measurement of attenuation, reflected power, and after that we have learned the measurement of frequency by the two methods, and after that we have learned the measurement of a quality factor of a cavity resonator. So, for the next section of the measurement, we will move towards the next part of the microwave measurement. Thank you for today's lecture.